Okay, now we're on recording number 5. Another kind of complex one, but hopefully I can break it down for you. I've turned a few pages ahead to around 119, 120 for some more pictures. Actually, 121 of synaptic transmission. So now we're going to go over, it says in the outline, neurochemistry, which is actually correct here. We're going to talk about some background with neurochemistry first. The first thing you need to know is that when you talk about neurochemistry, we're talking about how are neurotransmitters made and how do they actually work. Because we said at the end of the axon, there's a little gap, there's a synapse, and it's these little chemicals that allow things to work. So the way these chemicals actually work is you actually have to make them. You have to make neurotransmitters. So the first step, if you go down in the outline a bit in neurochemistry, is you have to make the neurotransmitter synthesis. So are you familiar with a few neurotransmitters? Things like serotonin, dopamine. Could you actually eat these products? Well, the answer is yes. They're actually available chemically. There are products that are called serotonin and dopamine. You could eat them, but they really wouldn't do you any good, because the molecules themselves are kind of large. And the problem that we would actually have is when chemicals like this are in your body, if you eat serotonin and dopamine, when they go up to your brain has something that protects it. It's called the blood-brain barrier. And the blood-brain barrier, it looks like there's a picture of this as well for your outline. Basically, it's a layer of cells that if you have big molecules going through your brain, they will just go through the blood and they won't get into the brain tissue. So it's a protective device because a lot of things that are toxic in nature are large molecules. Unfortunately, something like pot is very fat soluble, so it gets in very readily to your brain and then causes its biochemical effect, as we say. So anyway, you have a blood-brain barrier that kind of protects you in the brain. And as I said, the next thing, if we follow the outline here, is making a neurotransmitter. And I actually think I've provided a couple of handouts here on how you actually make a couple of very important neurotransmitters. So you could eat serotonin, but instead, neurotransmitters, when they're made, you have to basically take precursor products. So let's say you drink a glass of milk. Milk has a lot of tryptophan in it. And if you look at the biochemistry of serotonin, you can see that milk having tryptophan is taken up. It gets through the blood-brain barrier. It'll be converted from tryptophan by some enzymes into 5-hydroxytryptophan. And then from that, it'll be then converted into 5-hydroxytryptamine. And instead of calling something 5-hydroxytryptamine, we just give it the name serotonin. But the abbreviation for serotonin, and remember there's no A in serotonin, is 5-HT. Because it actually stands for 5-hydroxytryptamine. So serotonin is made from tryptophan into 5-hydroxytryptophan into serotonin. So you take the precursor chemicals and they're converted into that. So that's one example. The other types of neurotransmitters we know, if you look at the other handout, are called catecholamines. And if you look at the other handout, from your diets many times have a product called tyrosine in them. And tyrosine, when it gets through the blood-brain barrier, goes into the brain and it's converted into dopa. Dopa will then be converted into dopamine, and dopamine, if it has another chemical in it, can be converted into norepinephrine and then epinephrine. So these three, dopamine, norepinephrine, and epinephrine, are all considered catecholamines. Why? Because you're taking a catechol group and you're attaching it to an amine group. That's actually true. Sorry about that. So anyway, you basically use precursor chemicals to make neurotransmitters. Your body has them in your diet, and then they're converted into neurotransmitters. So the first big step in neurotransmission is you have to make these neurotransmitters, and that's by taking precursor chemicals. They are converted, synthesized into the neurotransmitter. And just to give you another example of this, remember we talked about Parkinson's disease before? People with Parkinson's disease lack dopamine. And so when people have Parkinson's disease, guess what product they are given? They are given L-DOPA, because if L-DOPA can get through the blood-brain barrier, which it does, it's converted into dopamine. So Steps in neurotransmission. We've spent some time here on synthesis. Let's keep going with the pipeline. So first you have synthesis. The neurotransmitter is made. Let's see what we've got next as far as a picture for you. I'm not seeing it quite the right way here, so let me just share it with you. After the neurotransmitter is made, it actually has to be stored. And the neurotransmitters are actually stored. If you look on page 125, 124, you can see that the neurotransmitters are stored in little pouches, if you will. Those are called vesicles. The neurotransmitters are stored in vesicles. Not at the beginning of the neuron, not near the dendrite or the cell body, but way at the end, at the bottom of the axon. So neurotransmitters are stored at the very bottom of the axons. So that's step 2 is storage. Now the next step is very, very important for our stories. Remember where we left the electrophysiology story? We left that story with the electricity coming down to the bottom of the neuron, the bottom of the axon. Well, this is where the two stories meet. When the electricity comes down to the very end of the axon, it actually impacts these vesicles. Now, not all of them, but just a handful of these vesicles. And when the electricity interacts with these vesicles, it causes the neurotransmitter to be released. So step 3 is release of the neurotransmitter. The neurotransmitter gets released into the synapse. And once again, if you watch the video or even look at these things, you can kind of see that going on. So step 3 is release. And when release happens, that release depends on electricity, so we say it's electrically dependent. You also need to have some calcium there. Now, not a whole bunch of calcium, and don't think loading up on calcium on the diet is going to be a good thing, but calcium needs to be there as well. So we say that this process of the release of the neurotransmitter is both calcium and electrically dependent. We give this a name because we can't have just release. That's no fun. We call this exocytosis. Exo meaning the neuron or the vesicle fuses with the membrane, exo, and releases the neurotransmitter out, so it's freeing the contents in the cell. So this is called exocytosis, and I think I have a picture of that for you as well. So now, what does the neurotransmitter do? It goes to the other side. Sounds like a Jim Morrison in the Doors song, right? Get on to the other side. Sorry, bad joke. Can't help it. Occupational hazard. So the neurotransmitter travels across the synapse, and then when it gets to the other side, what is on the other side? Well, that's the new neuron. It's the dendrite of the new neuron, and there's something very important on the side of that new neuron. There's actually little binding sites where the neurotransmitter will bind on what's called the receptor of the next dendrite. So the neurotransmitter will bind on the receptor of the next dendrite. And if you look once again on 124, 125, maybe the best picture that we're going to go into next is on the bottom of 125. It shows ionotropic and metabotropic receptors. And thank God you don't have to say these words in class, huh? I used to stumble on them. So the neurotransmitter will travel across. So it's actually the chemical that's traveling across and binding. Now when the neurotransmitter binds, the chemical doesn't really go into the next dendrite. Instead, when the chemical binds, a channel is reopened. So the way it actually works is the chemical binds and then a channel is opened post-synaptically, after the synapse. A channel is open, and depending on how and what happens when that channel is opened, the next action potential may occur. So if you look at that, you can see in A that a neurotransmitter is binding to the binding site, and then you can kind of see a channel is open, and depending on what happens with that channel opening will dictate what happens to the next neuron. So let me give you an example of this. There's a neurotransmitter in our system that's called glutamate. You may have heard of it. Glutamate? It turns out that glutamate tends to cause a lot of action potential. So let me give you the example of this. Glutamate is made and it's stored in the vesicles. And then an action potential happens. It'll be released. It will bind. And when glutamate binds, it does it through what we call an ionotropic mechanism. The glutamate will bind, and because glutamate tends to be kind of an excitatory type of neurotransmitter, when glutamate binds, it almost always opens up a calcium channel. And if a calcium channel is open, it almost always leads to a calcium influx. Calcium is Ca++. And so basically what happens, and you may need to listen to this more than once, when glutamate binds, a calcium channel is open, calcium will rush into the postsynaptic network. Now what do you think calcium does for the next dendrites? Hopefully you say that when calcium rushes in, it's a very positively charged ion. It's going to actually cause a lot of depolarization and lead to another action potential. And so glutamate tends to be an excitatory type of product. When glutamate comes in, or when glutamate binds, there's a calcium influx, and we actually give that postsynaptic receptor another term we use. If glutamate is binding and calcium is rushing in, we say when that postsynaptic neuron has a positive charge to it, when it's getting all positive, that is called an EPSP. No, that's not a sports news radio show. EPSP stands for excitatory postsynaptic potential, which should hopefully be in your book as well, because God knows I'm not making this up. So when glutamate binds, calcium rushes in, and when the calcium rushes in, it causes basically a depolarization, and that's the same thing as an EPSP, excitatory postsynaptic potential, which will lead the next neuron to have another action potential. So that's one example of an ionotropic mechanism. On the other hand, if you have another product like GABA, you may have heard of GABA. GABA is a neurotransmitter, GABA. When GABA binds, an ion channel is open for chloride. And chloride is Cl negative. And if it's Cl negative, then chloride will have an influx. And what will happen there? Well, it'll be very negatively charged postsynaptically, and that will basically stop action potentials from occurring. That'll cause what's known as an IPSP, inhibitory postsynaptic potential. And the next neuron won't fire. Now, you might be thinking, hey, I want my neurons to be working all the time, every time, but actually that's not the case at all with what we know about the human brain. For example, my daughter, who has epilepsy, it turns out when somebody has epilepsy, there's too much neuronal firing going on at once. It turns out that GABA is a very good substance to have a lot of in the brain, because the brain, if it had too much activity, there'd be a lot of seizures going on. So some of the products to help epilepsy actually get GABA to work better, causing more of a chloride influx. So that's called an ionotropic mechanism, because the neurotransmitter binds and quickly products come through, ions come through quickly. Another mechanism, and I'm not going to go into a lot of detail here, is what's called a metabotropic mechanism. In that one, a neurotransmitter binds, and then if you look at the picture here, a G protein is sent from one area, and actually a second messenger is sent to another area of the ion channel and opens it up. A second messenger system is at work here, like cyclic AMP. For this mechanism, it takes longer to have this happen, but when you're working with a second messenger system and it's metabotropic, when an ion channel opens for that, it tends to stay open longer. So ionotropic are quick and short-lived, and they happen very fast, whereas metabotropic, there's binding, and then it just takes longer to initiate it, but the channel stays open for a longer period of time. So we have ionotropic, metabotropic, we have channels opening, we have EPSPs, we have IPSPs that are all going on as well. And actually it looks like in the outline on page 2, I put EPSPs and IPSPs. If you get EPSPs, that's going to lead to another action potential, like glutamate binding. If it's GABA binding, it'll lead to IPSPs. So look at the video there as well, and hopefully this will make some sense. Now we're at the last step in the process. So we've hopefully sent another action potential or not, but then the question is, okay, the neurotransmitter is at this postsynaptic receptor. What happens next to the neurotransmitter? The last step in this process is what we know as inactivation. The neurotransmitter gets inactivated. There are two ways to do this. One way to do this is that an enzyme comes in, and an enzyme might come in and destroy the neurotransmitter. So if an enzyme comes in and destroys the neurotransmitter, then the neurotransmitter can't work anymore. For example, when acetylcholine binds, there's a enzyme that comes in after this. It's called acetylcholinesterase, and acetylcholinesterase breaks down the acetylcholine, and thus it inactivates it. So that's one way. A second way to inactivate a neurotransmitter is basically by what's called reuptake. And in reuptake, which is also somewhere here in your book, looks like 127, the neurotransmitter basically gets recycled back into the presynaptic area. So restored into the vesicles so it can stay there for another action potential. So this long recording basically covers the steps that we know as neurochemistry. So neurochemistry, how are neurotransmitters made? How are they stored? How are they released? The story of electrophysiology is very much linked to the story of neurochemistry, but a neurochemist studies the neurotransmitters, an electrophysiologist would be studying action potentials. Hopefully you have a good understanding of these two stories and can type up some good information here. Thank you.